Okay, so let's come back to our lecture. Okay, so we have finished our discussion about second order equations. So for the upcoming two lectures, I will be mainly talking. Okay, so I will be mainly talking about. Okay, so I'll be mainly talking about higher order equations. Okay, so higher order linear equations. Okay, so it will be higher order linear equation. So how are we going to consider a higher order linear equation? Well, that means previously our equation has been of the form. Okay, so has been of the form. For example, y prime. Okay, so plus p of t of y is equal to g of t. So that's the first order equation, right? So, but the general form of the first order equation is actually can take the form. Okay, so I mean it can take the form, for example, a1 of t of y prime plus a0 of t of y is equal to g of t. So that's kind of uh, the uh, I mean the form of this equation. Let me use p. Okay, so which is not in a standard form, but in a standard form it will like this. Now for the second order equations, we've been talking about, for example, a2 of t of y double prime, right? So plus a1 of t of y prime plus a0 of t of y is equal to b of t. So that's another scenario where you can consider. Okay, so where you can consider second order equation. And in standard form, it becomes y double prime plus pt of y prime plus qt of y. Okay, so plus qt of y is going to be equal. Okay, so it's going to be equal to g of t. Okay, so that's going to be the scenario. Okay, so that's going to be scenario. Now for higher order equations, we'll consider a very similar situation. Okay, so that means instead of first or second order equations, I'm going to consider the nth order equation. So that means a n of t y to the nth derivative plus a n minus 1 of t y to the n minus 1's derivative plus dot 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 plus a1 of t of y prime plus a0 of t of y is equal to b of t. Okay, so that's going to be like the non-standard form. But in the standard form, the equation is going to look like y n's derivative. Okay, so y n's derivative plus p1. So let me use p1 of t of y n minus 1's derivative. Okay, so maybe it's good to use p n minus 1. Okay, so plus dot 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 plus y. Okay, so p1 of t of y prime plus p0 of t of y is equal to g of t. So that's kind of the equation in a standard form, right? So by standard form, it means the leading coefficient is equal to y. Okay, so that's going to be several different scenarios. Okay, so for the higher order linear equation. So that's kind of give us a general picture of what is a higher order linear equation. How does it look like? Okay, so how does it look like? So let me now focus. Okay, so let me now focus on this higher order equation. Okay, so let me focus on this higher order equation. So let me say this equation, higher order linear equation that not in the standard form have this form a n of t y n's derivative plus a n minus 1 of t y n minus 1's derivative plus dot 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 plus a1 of t y prime plus a0 of t of y is equal to b of t. So that's going to be like this this equation. Now we can turn this equation in standard form by setting the a y n's derivative plus a n minus 1 of t. Okay, so divided by a n of t, right? So of y n minus 1. Okay, so plus dot 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 plus a1 of t divided by a n of t y prime plus a0 of t divided by a n of t of y is equal to b of t divided by an of t. So that's going to be the standard form is in an equation. So the standard form, okay, so the standard form is an equation of the formyn's derivative plus p of n minus 1 of t of yn minus 1's derivative, right? So plus dot 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 plus p1 of t of y prime plus p0 of t of y is equal to q of t, right? So or maybe I will use g of t. Okay, so maybe I'll use g of t. So that's going to be the standard form for this linear equation. Now the first question, okay, so the first question we would like to address is the existence and uniqueness. So remember, we've been talking about the initial value problems for second order and first order equations. Okay, so what are our theory? Well, our theory were stating that if you want to have existence, okay, so the existence and the uniqueness, okay, so if you want to have existence and uniqueness of your solution, then it suffices, okay, so then it suffices to first turn this equation in standard form. So the equation must be in a standard form before you can do anything. So by standard form, it means the leading coefficient in front of the highest derivative is 1. Okay, in that case, you're just going to look at those at those coefficients that are left. For example, is p, q, and g. If they are all continuous, then I'm going to have existence and uniqueness. So that's kind of the theorem that we've been talking about before. For example, here, if p, q, and g are both continuous, are all continuous functions, then you're going to have the existence and uniqueness of your solution. So the situation will be the same for higher order equations. But remember, you must turn the equation. Okay, so I will use black ink. You must turn this equation into standard form before you can do anything. So as long as you turn the equation in standard form, it suffices that all these p's, right, as well as the g are continuous functions. So that's going to be important. So that means all these p's, okay, so all these coefficients in front of those derivatives and y as well as the g has to be continuous. So let me say, okay, so all these coefficients, they have to be continuous, right? So all these coefficients, they're going to be continuous. Okay, so that's okay, so they have to be continuous in order to guarantee that you're going to have, okay, so you're going to have an existing uniqueness solution. But remember, you must turn the equation in standard form before you can do anything. Okay, so let's look at an example. Okay, so an example. So here it says that, can you define the largest interval I for which, okay, so for which the initial value problem, ty cubic derivative plus sine t of y double derivative plus t this blah, 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 is sure to have a unique solution. So if you want to look at this equation, first of all, you realize that it is not an equation in standard form. Okay, so it is not an equation in standard form, right? So let me put this equation into my okay, so into my lecture. Okay, so let's say we have this equation. Okay, so we have this equation, but this equation is not in a standard form, right? So it's not in a standard form, right? So you must realize that this is not an equation in standard form. Now, how do you make this equation into standard form? Well, the idea is very simple. So you can just divide by t. So that means the standard form, okay, so right, so the standard form of this equation is simply y cubic derivative plus sine t over t of y second derivative plus t squared minus 1 over t of y prime plus 3 over t of y is equal to tangent t over t. And in that case, you will need these coefficients, right? So you will need these coefficients to be continuous. So that means you want to avoid the singularity. So t cannot be equal to 0. But there is another singularity is by tangent t, right? So that means t cannot be equal. Tangent t will have singularities at k pi over 2, right? So where k is an integer, right? K is an integer. So t has to avoid both, right? So now if you come back to the question says, can you find this interval I? But you're starting initial conditions from 1, right? So You will start from the initial conditions from 1. So if you draw a picture, it will be something like this, right? So you want to avoid 0, right? So and then you want to avoid pi over 2. So pi over 2 is approximately, okay, so 3.14 over 2. So approximately, okay, so approximately 1.5 or something, right? So around 1.5. So it's a little bit larger than 1, right? So that's going to be, this is 1. So this might be pi over 2, right? So this is probably 1, etc. Now you want to start the initial value problem starting from point 1, right? So that means 1 has to be included in your interval, and you want to avoid 0. And so the largest interval is going to be the interval I, which is 0 to pi over 2. So that's how you determine the largest interval on which the equation is going to sure to have a unique solution. Is that good, family? Okay, so that's kind of the idea about existence and uniqueness. Remember, you must turn the equation into standard form before you can do anything. Okay, so that's going to be quite important. Okay, so now we're going to start talking about homogeneous equations. Okay, so remember when we were talking about linear equations, there are actually homogeneous and non-homogeneous, right? So these equations that have a non-zero right-hand side are non-homogeneous equation. If the right-hand side has turned to 0, then it's going to be homogeneous. Or more precisely, if there's no term that do not involve any of those y's, then this equation is going to be the homogeneous equation. Is it good, family? Okay, so that's going to be the idea. Okay, so that's going to be the idea. So let's talk about homogeneous equations. Okay, so homogeneous equation. So how do we solve homogeneous equations? Well, remember, if you have second order equations like y, let's say y double prime plus p, okay, so p1 of t, okay, so let's say pt, okay, so let's say pt of y prime plus qt of y is equal to g of t. Then our homogeneous equation theory says that you're going to create two solutions first, right? So these are the so-called fundamental solutions. Okay, so these are the so-called fundamental solutions, right? So by fundamental solutions, it means that the solution y1 of t, y2 of t, both are the solution. Sorry, this is homogeneous equation. Okay, so both are the solution to the homogeneous equation, and such that they are round skin. Okay, so we've been talking about this very important notion. Wronskian W of y1 and y2 is equal to y1, y2, y1 prime, and y2 prime. So that's actually y1, y2 prime minus the y1 prime and y2. So the Wronskian has to be non-zero, right? So if the Wronskian is non-zero, then we are going to say that these solutions y1 and t and y2 of t are linearly independent, right? So we're going to say that they are linearly independent. These are linearly independent solutions. As long as you have linearly independent solutions, you can see that the general solution, okay, so of the homogeneous equation, okay, so the general solution of the homogeneous equation takes the form yt is equal to c1 y1 of t plus c2 y2 of t. So that's going to be the way how you create a general solution to the homogeneous equation. Is that good, family? Okay. So now the point here is that we have to extend, right? So we have to extend the whole theory to higher order equations. Okay. So what happened here is that if you consider higher order, let me use let's say higher order. Okay. So let me use the equation in standard form. So that means n's derivative. Okay. So plus. Okay. So p. Let me say pn minus 1 of t y n minus 1's derivative plus dot dot dot. Plus p1 of t of y prime plus p0 of t of y is equal to 0, right? So that's going to be higher order homogeneous equation. Then you're going to create a set of fundamental solutions. Okay, so fundamental solutions, let's say fundamental solutions, right? So then you're going to create a set of fundamental solutions. But how many fundamental solutions you need? Well, previously it was 2 because you have a second order equation. So that means you're going to just create y1 of t, y2 of t until you get yn of t. Is that good for everybody? Okay. How are you going to justify that they are a fundamental solution? Well, that means you have to consider the Wronskian W of y1, y2 of yn. This is not just two functions, but n functions. So the n functions, the Wronskian will be the same thing. So that will be the determinant. Okay, so that will be the determinant y1, y2. Okay, so of yn, and then the second row are the, as before, are the derivatives. So y1 prime up until you reach yn prime. But then this is not a square matrix. In order to reach a square matrix, how many derivatives you need? Well, you have to reach n minus 1's derivative and y2 of n minus 1's derivative until you reach yn of n minus 1's derivative, right? So because the first row is other zeros derivative, and in order to have n rows, you have to reach n minus 1's derivative. Is that good, family? Right? It is a kind of course, a little bit intimidating, right? So that we are calculating a determinant of this huge size, n by n. But here previously it was 2 by 2. It was easy to calculate. Everybody knows how to calculate it. Is that good, family? Okay, so but you have this definition. So let's say formally, if the Wronskian is non-zero, then we're going to say y1, y2 until you reach yn are linearly independent. Right, so these functions are going to be linearly independent, right? So that's going to be like what we said before, they're linearly independent. And then you're going to say that the general solution, okay, so the general solution, okay, so the general solution is going to be the solution y of t is c1 y1 of t plus dot 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 plus cn yn of t. It's just a linear combination of those solutions, y1 of t until you reach yn of t. Okay, so that's going to be your scenario. Okay, that's going to be. So that's kind of the, we will call it theorem. This is about second order equation. You just want to create a Wronskian that's non-zero, then you do a linear combination. Now you have the same thing. So you have the nth order equation. You just want to have a family of solution that's a linear combination of the fundamental solutions. This is true if and only if the Wronskian is non-zero and you have a family of linear independent solutions and the general solution are just linear combinations. So this is kind of a natural, okay, so very natural and naive extension of what we have been doing before. Okay, so that's kind of a very natural and naive extension of what we have been doing before. However, such an extension has problems, right? So raises some problems and concerns that we have to be fixing, right? So what are these problems and concerns? Well, problems and concerns are the following. So first of all, what does it mean? Okay, so what does it mean, the Wronskian, right? So what it means by calculating, so what does it mean, the Wronskian? This calculation is a little bit kind of unusual because it has to calculate such a huge matrix and compute its determinant. This what we don't know how to do it, right? So that we have to specify. And the second thing is that what does it mean these functions are linearly independent? Because previously linearly independence is like if the Wronskian is non-zero, then linearly independence. But we are going to say that linearly independency is going to have another meaning, which is kind of let's say which is kind of more close to its name, linearly independent. Okay, so that's kind of, these are the two things that we're going to fix. Okay, so that's two things that we're going to fix in the upcoming time. Okay, so now let's look at the Wronskian first, right? So let's look at the Wronskian first. So the Wronskian is going to involve a determinant. Okay, so the Wronskian is going to involve a determinant. For two functions, it is easy to calculate this determinant, right? So let's say the Wronskian of y1 and y2 is just equal to, let's say sometimes we use determinant of y1, y2, y1 prime, y2 prime. This is the matrix that we are going to calculate determinant. Or you may use two long lines. Okay, so y1, y2, y1 prime, y2 prime, that's also determinant. But what it means by this determinant is just the y1, y2 prime minus the y1 prime and y2. So you just do a cross of these two corresponding two terms, and you do a minus sign. Okay, so that's the determinant. So the problem is that how do you calculate w, y1, y2, and y3? Let's say you have three functions. Then you're going to reach determinant. I mean, you can write determinant, or you can write two long lines. I'm going to just use two long lines. So that's y1, y2, and y3, y1 prime, y2 prime, and y3 prime. and y1 double prime, y2 double prime, and y3 double prime. So that's going to be the determinant that you would like to calculate. Now, how are you going to calculate this one, right? So the house 3 by 3. So that's kind of the scene, okay? So that's kind of the scene that we would like to talk a little bit in this lecture. Okay, so maybe I'll take a few minutes, right? So determinant, okay, so how do you calculate determinant of 3 by 3 matrices, right? So if you have a 3 by 3 matrix, so that might look like A11, okay, so A12 and A13 and A21, A22 and A23 and A31, A32 and A33. So that's a determinant of a 3 by 3 matrix. Now, how do we calculate it? I'm going to give you two ways to calculate 3 by 3 matrix. The first way is what we call it the direct method. Okay, so direct method simply goes as follows. Okay, so you're going to put this matrix. Okay, so A11, A12, A13. Okay, so A21, A22. Okay, so A23 and A31. Okay, so A32 and A33. You're going to put it in a matrix. Okay, so in a matrix. Now, once you put in a matrix, you're going to go from the upper left corner to the lower right corner and write a plus sign for the product. So what does that mean? Well, that means, so let me use blue ink. Okay, so that means I'm going to do these three terms. And once these three terms are there, I'm going to product them. So if I product them, I'm going to reach A11, A22, and A33. So that's a plus sign. Okay, so that's a plus sign. Then I'm going to do the same story. Okay, so do the same story. I will reach these two terms, right? So you're going to consecutively use each of these terms in the first row. So once you have these two terms, you see there is one term missing here, right? So because you want to kind of cross out and you want to have two parallels. So what's the term here? Well, the term here can be determined by imagining that you have a copy of this matrix on the right-hand side on the right side of the original. So that means A11, A12, and A13. Okay, so A21, okay, so A22 and A23, and then it's going to be A31, A32, and A33. So that's going to be a copy of the original matrix, and that will reach, okay, so that will help you, the blue arrow, to reach the term that you need. So that's going to see, from that, you're going to see that the second term with a plus sign is A12, okay, so let's say A23, right? So, and A31. So that's going to be these three terms. And similarly for A13, you're going to start from A13, you go to the from upper left to lower right, and you immediately exit the matrix, you reach the outside matrix. So there are two terms, A21 and A32. So that being said, okay, so that being said, you're going to see that we're going to have, okay, so you're going to see that we're going to have plus, okay, so A13, A21, and A32. So these are really those terms that should be with plus signs. Okay, so these are those terms that should be with plus signs. What about minus sign? Well, the minus sign goes in the reverse direction. So it goes from the upper right corner to the lower left corner. So that means you're going to go this way. Okay, so you're going to go this way. As long as you go this way, you're going to see that these are with minus sign. So minus A13, A22, and A31. Okay, so that's the first minus. And then you're going to have the similar problem. If you start from here, okay, so you start from here, you go to the lower right corner, you're going to exit the matrix. So what should you do? Well, you're going to have another copy of the same matrix. So that means A11, okay, so A12, A13. So you just move this matrix to the left. Okay, so then you're going to have A21, A22, and A23, and A31. Okay, so A32 and A33. You move this whole matrix to the left. As long as you have moved this matrix to the left, then you're going to take these two terms and exit the matrix. You reach this term. And you're going to start from here. You take to the lower right corner. You're going to exit the matrix. You reach these two terms. Is that good, family? Okay, so as long as you have those, you can calculate this products. So that's going to be minus A12, A21, and A33. and minus the A11, A23, and A32. So all these terms are accompanied with the negative sign. Okay, so all these terms are accompanied with the negative sign. So that's going to be how you are going to look at this whole problem. Okay, so however, people usually, okay, so people usually consider, okay, so consider if you are very familiar with this calculation, you don't have to spend time to write, okay, so you don't have to really spend time to write the two copies on the left and right side of the original matrix. You can work within the original matrix. For example, for plus signs, you can see that these three are going to be producting. And once you product these two, you see you come to A31. A31 is just here. So you can just move to here. Is that good for everybody? Okay, so and then you're going to have these two terms, and you're going to just move to here. So that usually people say A13 is moving this direction, A21, A32 is just these two. So you can, these are the trajectories for plus signs. And what about minus sign? Well, minus sign, you're going to see that at first you're going to go this way, right? So these three terms are going to product each other. And then once you product these two, okay, so once you product these two, okay, so you're going to wind to here, right? So because you product these two, then you're going to have A33. So you're going to reach here, okay? So that's going to be these two. And what about this one? Well, this one, you're going to go in this direction, directed to here, and then go to here, right? So because A11, next term is A23 and A32. So that's the way how you are going to just work within one matrix. Okay, so that's the way how you're going to work just within one matrix. So that's the way how you calculate the determinant of 3 by 3 matrix. Such a method is called the direct method. Okay, so such a method is called the direct method. Okay, so this method is going to be called the direct method. So we're going to introduce another method. Okay, so we're going to introduce another method, which we're going to call it the Laplace method. Okay, so the Laplace method. So what is the Laplace method? Well, Laplace method is an expansion method. So A11, A12, let's say A13, right? So let's say A21, A22. Okay, so A23, right? So A23. And as well as, okay, so as well as A31, okay, so A32 and A33. That's going to be this, how do you do the Laplace method? Well, the Laplace method means that you're going to pick either, any of these rows or columns. Okay, so for example, let me just put the first row. Okay, so I pick the first row here. So once you pick the first row here, the expansion is going to be like A11. Okay, so plus the product, some product of A12, and let's say plus some product of A13. Okay, so that's going to be, this is why it's called an expansion. Okay, so now with this expansion at hand, what you're going to do is that say you fix A11, you want to expand with respect to A11. Then what you're going to do is that you're going to look at the row containing A11. Then you're going to look at the column containing A11. And you're going to delete this row and this column. So the resulting matrix is this one. Is a good for everybody? Okay, so the resulting matrix is a 2 by 2 matrix. It's sometimes called a minor matrix. Okay, so sometimes called a minor matrix. Once you have the minor matrix, you're going to just calculate a determinant of the minor. So that's going to be A22, A23. Okay, so A32 and A33. So that's going to be the minor matrix. And similar thing for A12 and A13. The only thing you have to do is to determine your minor. For example, for A12, how do I determine the minor? Well, the A12 contains this row, column is this column, row is this row. So you delete the column and row, the resulting terms are these two terms and these two terms, because this one is deleted, this one are deleted. And you're going to use them to form a matrix. So how do you form a matrix? Well, you can just imagine that there are no other terms like in the middle. So that means it is going to be A21, A23, like A21 is here, A23 is here, as well as A31 and A33. Is that good for everybody? Okay, so I'll leave it to you as an exercise to check that for A13, the resulting terms. Okay, so For A13, the resulting terms are, so it's kind of, you just delete A13, you just delete this column. The resulting terms are these 4 terms. Is that good, family? Okay, so as long as you have these 4 terms, then you're going to have A21, okay, so A22 and A31 and A32. So that's going to be your matrix. Okay, but however, this is not direct expansion, but the point here is that here we have to multiply. Okay, so we have to multiply signs. So there are sign issues, -1 to certain power. So I claim that this is 1 plus 1, -1 to the power of 1 plus 2, and -1 to the power of 1 plus 3. So there has to be certain signs related to each of these expansions. And how do you determine the sign? Well, you see, A11 is the first, the element in the first row and first column. So you're going to use -1, the number of row plus the number of column. So that's always -1 to a power, but the power is equal to the number of row plus the number of column. Okay, so that's kind of the, so here you can see this power is the first row, second column, and first row, third column. So it's always the number of row plus number of column. However, if you have -1 to the power of 2, it's just 1. This one is -1 to the power of 3, is actually -1. And this is actually, so in the end, you're going to have A11 just multiplied by A22, A23. Okay, so dot, this derivative, minus the A12. And then I'm not going to fill in here, it's just a take copy, plus the A13. And then you're going to calculate these copies here. So that's Laplace method. Is a kind of a nice method. It can reduce the calculation of the determinant of 3 by 3 into the determinant of 2 by 2. Each of these determinants are possible to be calculated. And once they're calculated, you can just multiply them by the corresponding row or column that you choose. So the Laplace method works for, here we are working the Laplace method for just one row. You can actually pick arbitrary row or column, but you have to remember that first of all, you have to calculate this minus. This minus have to be calculated. Second thing is that there has to be a sign, which is just a -1 to the power of the number of row plus the number of columns. So that's going to be important. Okay, so I'll leave to you as an exercise to justify that after further calculations, I mean, you expand these 2 by 2 matrices, and you do the product, it is going to agree with our direct calculation of the determinant of 3 by 3 matrices. Is that good, everybody? Okay, so that being said, we come back to this round scheme. Now you can see that this is just calculating the determinant of a 3 by 3 matrix. So we can really do it, right? So we really know how to do it by just saying that this is actually y1, y2 prime. So let me you can actually draw these arrows by yourself. Okay, so and but if you're very familiar with it, then you can read the values out. Okay, so here let me, because we are beginners, let me draw these arrows, right? So these are plus arrows, and then I'm going to have the next stage of the plus arrows are going to be like this, and the next stage of plus arrows are going to be like this, right? So if you remember, and for the negative arrows, there's first stage of the negative arrows is going to be this this one, right? So and then the negative arrows are going to go this way, and you're going out, so you're going to kind of wind it to here, and then you're going to come here, directly wind to here. So that means the next stage of those is something like this. Is that good, family? Okay, so as long as you have all these arrows, you can calculate. So that's y1, y2 prime, and y3 double prime, and plus the y2, y3 prime, and y1 double prime, and plus this 3. So that's a y3, y1 prime, and y2 double prime. So, and then it's subtracting. Okay, so it is going to subtracting those red arrows. So that's y3, y2 prime, and y1 double prime. And you have this 3. So that's minus y2, y1 prime, and y3 double prime, and minus this y1, y3 prime, and y2 double prime. Is that good, family? Right? So that's going to be how you calculate the 3 by 3 determinant for the round scheme. So that's going to be the point here. Okay, so that's going to be the point here. So you can actually calculate this round scheme. I mean, as a determinant of 3 by 3 matrices. Okay, so if you're interested, you can also use the Laplace expansion and see how this round scheme can be calculated. Okay, so and see how this Wronskian can be calculated. Okay, so that's settles our first problem is about how this multi-dimensional Wronskian can be calculated. The second thing is about the linearly independency. Okay, so the second thing is about why these functions are linearly independent, right? So where does this notion come out, right? So where does this notion come out? Okay, so now let us look at the linear combination. Okay, so let us look at the linear combination. Okay, so for example, here there is actually a formal definition of linear independency, but a little bit different from what we have been learning before. But this is going to be very important and a little bit hard to understand. Okay, so I promise you it will be a little bit hard to understand because it's a little bit algebraic. Okay, so what happens here is that so we have a definition. Okay, so we have a definition of linearly independent. So we say, okay, so we say functions. Okay, so we say let's say functions. Okay, so we're going to say that the functions f1. Okay, so let's say f1 of t until you reach fn of t are linearly independent. Okay, so are linearly independent. Right, so we say these functions are linearly independent if and only if. Okay, so if and only if you're going to say that if and only if for any, okay, so for any this sequence k1 of kn such that okay, so k1 f1 of t plus dot 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 plus kn fn of t is equal to 0 is going to imply, okay, so implies that k1 is equal to k2 is dot 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 is equal to kn is equal to 0. Okay, so if and only if, okay, so okay, so I mean, so let me say let me raise this full. Okay, so that kind of says that if and only if that if you have any k1 and kn, okay, so if I want this identity k1 f1 plus kn f1 is equal to 0, then it is going to imply that k1 is equal to k2 is equal to kn is equal to 0. Okay, so all these cases are equal to 0. Otherwise, okay, so let's say otherwise we say, okay, so we say the functions f1 of t until you reach fn of t are linearly dependent. Okay, so they are going to be linearly dependent. So that's the difference between the linearly independent and the linearly dependent functions. So this notion is a little bit kind of weird, right? So because it's kind of not related to the Wronskian. Previously, we were talking about the Wronskian, and now it's, seems to be nothing related to the Wronskian. So it just says that if you have a linear combination, so basically in terms of simple symbols, it just says that if the linear combination k1 f1 plus dot 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 plus kn fn of t is equal to 0, it just implies that k1 is dot 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 is equal to kn is equal to 0. So that's linear independency just means this, right? So let's say linear independence. It just means this. And why is this true? Well, if you think of this equation, okay, so if you think of this equation, then let me write this equation in this form. f1 of t multiplied by k1 plus dot 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 plus fn of t multiplied by kn is 0. Then I'm going to see that if this is identity, then f1 prime of t multiplied by k1 plus dot 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 plus fn prime of t multiplied by kn is also equal to 0. Right, so and you can keep taking those derivatives until you reach the n minus 1's derivative of k1 plus dot 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 plus let's say f. Okay, so let's say fn of the n minus 1's derivative of t of kn is equal to 0. Is that good for everybody? Okay, so I mean these are direct consequences of the first identity, because if first identity is 0, you can keep taking those derivatives. Now, as long as you have this, you can see that we can treat this one as a linear system of equations for k1 up to kn. So what this means is that I'm going to treat, okay, so I'm going to treat this f1, f1 prime until fn, fn prime. These are we're going to treat as coefficients. Okay, so this is a coefficient of a system of linear system of equations where from which you want to solve for K1 and Kn, right? So K1 and K2, you solve for Kn. Is that good for everybody? Okay. So now linear independency says that the only solution is K1 is 0, K2 is 0, Kn is 0. So that means the system of linearly, the linear system of equations is going to have all the solutions to be 0. But on the other hand, you can justify that if you put all these coefficients to be 0, it is automatically a solution. Is that good for everybody? So what we say is that K1 is equal to Kn is 0 is always a solution. Right? So it is always a solution. I mean, this is very trivial because if you put all these zeros there, it is automatically going to result in a 0 on the right-hand side. So this is always a solution. So what does this linearly independent say? It says that if you have these identities, then it will imply that the K1 and Kn are always 0. So what does it mean? It means that this 0 is the unique solution. So the linearly independency, okay, so linearly independency is just going to say that it is also, okay, so it is also unique. It is also a unique solution. So that means the 0 solution, it is also a unique solution. So it is not only a solution, but a unique solution, which means that you can deduce that this must be zeros. But if these solutions are not unique, then it might happen there are other solutions. When do we have, if you have a system of linear equations, when is it going to guarantee that unique solution? The unique solution, okay, so the unique solution is being guaranteed if the coefficient matrix f1 of t fn of t, right? So these are the coefficients because in this problem, these coefficients are now the functions. So these coefficients until f1 n minus 1 of t fn of n minus 1 of t, these coefficients has to form a determinant, and we must guarantee that this determinant is non-zero. So that's kind of a little bit weird here. So in order to guarantee a unique solution, which is the 0 solution of the linear system of equations, you just need the coefficient matrix to form a determinant that is a non-zero. Okay, so the 0 and non-zero here are a little bit weird to understand, but you have to understand them. And what is this? Well, this is just nothing but the Wronskian between f1 up to fn. So that actually concludes our problem. Okay, so our problem, our observation is that the linearly independency. Okay, so linearly independence. Okay, so linearly independence of the functions f1t up to fn of t is the same thing as saying that any k1 up to kn such that k1 f1 of t plus plus kn fn of t is 0 implies, okay, so here I would say implies that k1 is equal to kn is equal to 0. So that's the first conclusion, but it is also sufficient to say that the Wronskian f1 of fn, which is the determinant f1 up to fn, and you reach f1 n minus 1's derivative up to fn n minus 1's derivative has to be non-zero. So that's kind of the two equivalent formulations. Okay, so first equivalent formulation says that any linear, so this is actually a linear combination, right? So this is actually a linear combination. So that's why this notion is called linearly independence, because it says that any linear combination is 0 implies all the coefficients are 0. But on the other hand, after our deduction here, it also says that the Wronskian has to be non-zero. So that actually explains this result that when we say you find these solutions y1, yn, then the Wronskian is non-zero. It simply means that they are linearly independent. Okay, so and they are linearly independent. So that's going to be another important thing that we want to address in today's lecture is about the linearly independence. Okay, so if you formulate all these theorems. Okay, so in the theorem, so it says that if you have n such fundamental solutions, they're going to be linearly independent if and only if the Wronski is non-zero. Okay, so here I would like to show you a nice exercise. Okay, so here I have three functions, 1, t, and t squared. Are they linearly independent? Well, how do we check them? Well, there are two ways to check them. The first way is calculate their Wronskian. Okay, so and the first way is calculate their Wronskian. And the second way is to check that if the linear combination is 0, then you're going to see that the linear combination is going to just give you a polynomial of second order. It is equal to 0, which means that I mean, if you have a polynomial of second order that's equal to 0, then all the coefficients are 0. So it indeed is true that any linear combination is 0 implies that the coefficients are 0, right? So and therefore they are linearly independent. Okay, so therefore they are linearly independent. Okay, so that's kind of the linearly independency. Okay, so that's kind of the linearly independency issues. Okay, linearly independency issues. Here I would like to show you just one more example. It is about this existence uniqueness. Okay, so exam 2 for semester 2013. Okay, so for semester 2013. Okay, so let me see. Okay, so 2013. Okay, so and you can see that from time to time, people would like to test you about existence and uniqueness also. Okay, so if you look at this problem, you can see that this one is okay. So just one moment. Okay, so exam 2, number 5, right? So problem number 5, it is going to be about this linearly independent solutions. Okay, sorry. So this is another question about a set of functions that are linearly independent or linearly dependent. Okay, so as we just said in this lecture. So what you want to do is that you put these three functions there. There's three functions there, and then you calculate determinant. Okay, so a determinant is 3 by 3. As I just talked about in this lecture, you have to know how to calculate 3 by 3 determinants. And as long as you calculate those determinants, you find they're 0. Which means that if the Wronskian, okay, so you can, it is just a little bit hard to memorize here, but you have to understand it. And if the Wronskian is 0, then it means that they are linearly dependent. If the Wronskian is not 0, then it's going to be linearly independent. Is that good for everybody? Okay, so this is a kind of nice example. Another way to solve this problem is to consider a linear combination and prove that the linear combinations are 0. Okay, so I would strongly urge you to take a careful look at this problem and understand how one solves it. Okay, so that's about this linearly independency and linearly dependence. Okay, so therefore our question. Okay, so our question about the theory of first order equation, I mean higher order equations, is being addressed. Okay, so the only problem left are like how do you solve the homogeneous and non-homogeneous equations, right? So how do you solve homogeneous and non-homogeneous equations, right? So therefore it's good to remind you that if you want to have non-homogeneous equations, then you want to work with the so-called complementary equation. By complementary equation, it means that you have the right-hand side to be 0. And as long as you have complementary equation, you would like to just find a particular solution. And as long as you have the complementary solution and the particular solution, you can combine them. That's a general solution for the non-homogeneous problem. So the only problem here are two problems. The problems are, first of all, how do you find the fundamental solutions? If you have a higher order equation, how are you going to find fundamental solutions? The second question is, if you have a higher order non-homogeneous equation, how do you find these particular solutions? As long as you solve both of these questions, you can combine them, and then you're going to have general solution for the non-homogeneous problem. Okay, so these are going to be the themes of our upcoming lectures, during which we're going to discuss all these kind of problems. Okay, all these kind of problems. So that's what I want to say for today's lecture. Okay, so let's come back to the next lecture, and we will continue. Okay, so we will continue with this class. Okay, so let's meet you in the next lecture. Okay, so that's what I want to say for today's lecture, and see you in the next lecture.